Good evening. We have just a little under 10 minutes until tonight's puzzle for Advent of Code unlocks. We're going to be doing day 8 tonight. As always, going to be working in C++. If you have any questions or just want to say hi or anything, feel free to drop those in the chat. So while we're waiting for tonight's puzzle to unlock, I wanted to cover a few revisions I made to our solution for last night's puzzle. So one thing that you can see here is I wasn't very happy with the string parsing code we had to parse out the rules for what bags can contain other bags in last night's puzzle, the day 7 puzzle. So because we kind of combined approaches, we split strings by comma delimiters, and then we regex part of them, but other parts we split with different delimiters. It was kind of a messy mix of approaches. So I decided to clean that up a little bit. I made the shared rule parser library that both of the parts of the solution can use, and basically it parses out from the lines in the input file. So if we look at the day 7 input, we have lines like this. We have some color of bags, and contains, and then a list of the bags they can contain, or they can contain no other bags. So we want to parse that into a structure that we can actually use in our program. So we've got the container color for the outer bag like here we'd have dull green, drab lime, all these examples. And then for the contained bags, we have the color of those contained bags and the number of those bags that have to fit in there. So to implement this, I used the RE2 regular expression parser library. And I use this much more consistently. So the first thing what really made this a lot cleaner to use was using the consume function for RE2. So what we can do is we can snap one of these string pieces. A string piece is really exactly like a string view. It exists for the same purpose. It does the same stuff. It's just specific to the RE2 library. So with this consume, what we do is we consume the first chunk of the string of the string piece and adjust it to point to the first byte after that chunk. And so what we would do first here is match any number of characters, but it's any characters dot star is any number. The question mark here makes it non-greedy though, so that we want to find this bags contain substring. So we match the minimum number of characters until we get to bags contain here. And so we match that first. We get the color of our container on the outside. If the end of the string after that is no other bags, that a particular color of bags doesn't contain anything else, then we're done. There's nothing to say that it contains. Otherwise, we just do this loop and we parse clause after clause with this different regular expression. So this regular expression, what we're looking for is one or more digits to represent a count, like for example here 4 in plaid crimson bags. Then again a non-greedy string up to the point where we have space, and then bag. And then for S we have a question mark after that because it's optional. It could be bag or bags depending on if it's one or more than one. And then finally here we have this question mark colon is for a non-capturing alternation group, meaning that even though it's in parentheses, we don't actually want to match it to a parameter that we're providing to RE2 to read it out. We don't actually care about capturing it. We just want to, use parenthesization to group things. And so one of these clauses for a contained bag can either end in a comma and a space because there's going to be more in the string, or it'll end in a period because it's the end of the string. We don't care which one, we just care that one of those matches. So again, while that the remaining text in the rule that we're trying to parse is not empty, we just keep trying to parse the count from those digits, the color from this substring. We check that it matches, and then we add another entry to the contained bags here in bag rule. So I think that just using regular expressions consistently for everything and having just this one loop and not doing a bunch of stuff with trying to split strings by different delimiters, I think this is cleaner. I think this is nicer parsing, and so I went back and I incorporated that into the solutions for both parts. And so basically all of the stuff that is actually about graph traversal, about finding, the transitive closure going from the contained by or the contains relationship one way or the other, that is all the same as before. It's just that now we rely on this parse bag rule function that I just showed you in order to do all the parsing, and so we just put those into this bag graph implementation. We build up that same contained by map that we talked about in yesterday's stream, and this count outermost bags function is exactly the same as it was before. For part 2, very similarly, we're building up the contains map by just filling it in with the parsed rules from our function, and count held bags works basically exactly the same as it did before. So those are the revisions to yesterday's. Like I said, string parsing is cleaned up some more. I'm getting. I would say that actually parsing the input was the more challenging thing for me yesterday, and maybe if I took a little more time to think about, okay, how do we do this with just regular expressions, I probably would have gotten further along with it more quickly. But I'm glad I went back and fixed that. So we have about 2.5 minutes until today's puzzle unlocks. So I am going to go ahead and set up just the scaffolding for a new day's worth of puzzles. So we'll call this one day_08. We will make our bare bones executable. We will make our build file to let the Bazel build system know how to build this executable. Just for all the people joining the stream right now, always feel free to drop any questions in the chat if you have them. So now we're just about ready to go, with about 90 seconds left until tonight's puzzle unlocks. So yeah, we're starting to get some slightly more complicated puzzles. I think last night having to figure out transitive closures of graphs was pretty fun. And yeah, I like it that we're moving more towards puzzles that are sort of about figuring out the right algorithm as opposed to the difficulty being in string parsing. So we have just under a minute until the puzzle unlocks. Okay, what do we have today? Handheld halting. Flight to the major hub reaches cruising altitude without incident while you consider checking the in-flight menu for one of those drinks. You're interrupted by kid sitting next to you. Oh, his game console won't turn on. There's an infinite loop in the boot code of the device. But first we need to be able to run the code in isolation. Ooh, we have a little miniature assembly language. Fun. So we have one instruction per line. So we have an operation, accumulate, jump, or no op, and an argument, which is a signed number. So there's a single global value called the accumulator, and we increment or decrement it when ACK is called. Okay. Jump jumps to a new instruction relative to itself. For example, jump plus 2. Okay. And NOP stands for no operation, it does nothing. Okay. So, let's see. Looks like NOPs have arguments too, even though they don't actually do anything with them. Jump plus 4. Okay. With this sequence of loops, program will jump forever. The moment the program tries to run any instruction a second time, you know it will never terminate. Immediately before the program would run an instruction a second time, the value is 5. Okay, so we have to parse the boot code. We have to find the first time that it hits a line that it has already run before. So, I'm going to make a parsed version of the instruction that is a little easier for us to deal with, although we could easily go ahead and just run it on the strings directly, but, you know, I feel like doing it this way. So we'll say have an enum for our possible opcodes, and the possible ones are accumulator, accumulate, jump, and no op. So over here, yeah, I've started this struct for instructions, and we've got an enum for opcodes in it. So we'll just put in the cases for ACC for accumulate, JMP for jump, and NOP for no op. Actually, I'm going to put this enum class in the global scope just so we're not, always referring to instruction : opcode : whatever, just so we can be a little more terse with it. And argument is 0. We'll have a parse instruction function. And, as much fun as we've been having using regexes lately, this is simple enough that I think scanf is totally appropriate. So, oh, we forgot to actually include that there. Didn't autocomplete for some reason. Or I didn't tab complete it, so it didn't. So we want to parse the instruction string. We we'll have this buffer for the opcode string, so that's going to be 3 characters because all of the opcodes are written as 3 characters, and then 1 more character for a null terminator. So the format is going to be 3s space, and then there's going to be a plus or a minus, and then I think, just those both count as signed integers, so we can do that as d. Is that? Oh, I call it data instead of cster. And then we will. So we'll read that first string argument into opcode stir, and then we will read the digit directly into the argument string, the argument integer in the parsed version. Need to include the header for our check macro. So then we'll say if we are doing, because this is a C string, I mean, I suppose we could convert it to like a string view and check it the other way. Maybe we want to do, we'll just use strcomp. I already started writing it this way. I'm doing this in kind of a very low-level C-ish way using scanf and strcomp tonight. Basically the same pattern. I'll even copy and paste it for no op. Of course, if it doesn't match any of those 3 possibilities, we have a problem. It's not a recognized opcode. And then we'll say run program until loop. And our program will be a vector of these instructions. I'll pass that as a const reference. So we start with the accumulator at 0. We then we need to keep track of which lines in the program we visited, so we'll just use a set for that, flat hash set specifically. And now what we will do is run through the program. So we'll do our own infinite loop, but we'll have an exit condition in here. So equals 0. So what we're going to do is first thing we're going to do is try to put the current instruction number that we're executing into the set. So if we find that it's already present in the set, we know that we've entered into a loop and it's time to spit out the value of the accumulator. So if we can't insert the current instruction's address, then that means we've hit the end of the loop and we should return the current value of the accumulator. On the other hand, if this is our first time visiting the address, then we just execute it. So we should switch on the value of the current instruction's opcode. So we would say switch program current instruction dot opcode. Now, if it is accumulate, oh yeah, we just need to, it's just saying that we need to handle all of those cases, which we will. We will say accumulator plus equals, you know, I'm going to go ahead and make a copy of that instruction so that we have something shorter to refer to it by. Oh, and we would also go to the next instruction after that accumulate instruction. So in case of a jump, we don't do anything to the accumulator, but the current instruction we adjust by the argument. It's always relative to itself, so there's not an implicit one added to that. And for a no-op, we just go to the next instruction. Okay. I think this is our solution for part 1. Well, except that we have to actually add I/O. So check that we get 2 arguments, the name of the program itself and the name of our test file. Read our inputs. And then we will parse all of those into our instructions. Going to put in a little reserve there just to be extra efficient. Totally not necessary for correctness, but that will mean that the vector only has to allocate memory once and will never have to resize itself as we're building up that program memory. And then we will spit out the result of running the program until we find ourselves in an infinite loop by visiting the same instruction again. So we just need to add our dependencies. We need flat hash set, we need strings, we need check and I/O. So we're going to shamelessly borrow from the deps that we put together for yesterday's. And we want, this is almost what we need, except we want flash hat set instead of flat hash map. So I am going to take the example program that they gave us in the puzzle and just so that we can just verify that our program works as expected. So we're going to change this to day 8, part 1. And then on our test input, okay, it says 0. That is not correct. The correct answer for the value of the accumulator should be 5. So let's look at what could have gone wrong here. Everything seemed to parse correctly. I wonder, though, I wonder if the numeric arguments are getting properly parsed. Let's just spit those out here and see what they look like. Okay, those look correct. So how about now every time that the accumulator changes, that we hit an accumulate operation, I'm going to go ahead and spit out the value of the accumulator. Okay. So start 0. Goes to 4. And then is 0, 0, 0 until we get to the end. So we're saying immediately before the program would earn value in the accumulator is 5. Let's just have, for now, I'm just going to have the program kind of walk through the instructions as it's executing them. Yeah, because I'm not sure. Yeah. We'll just step through this in the same way that the program is stepping through it to see what's going wrong here. And not that the arguments for no ops matter, but we'll just see what that looks like. So, Something is up with the no-ops. That's weird. Because we would expect it to hit these no-ops. But everything looks like it's accumulated. Do we? What is going on here? Let's spit out the parsed program and see what it looks like, and make sure that we've got it right. So. Man, I thought this was going to be easy. I must be missing something basic, and once I figure it out, I'm sure I'll be kicking myself. I'll just put another new line so that it's separated from the rest of the stuff. Okay. Yeah, there's definitely something wrong with the parsing. So what we should have is no-op 0, accumulator 1, jump 4. Is everything off? These should be equal 0. Oh my gosh. I'm sorry, people. See, this is this is why you you should actually have practice using old C-style stuff before you actually try and use it, because I was treating those just like they were equality, and I'll bet the whole thing runs fine this time. Yep, everything's fine. Oh my goodness, people. Okay. I really serves me right for trying to do things in the really old school way. But that with that parsing problem solved, see, it's always getting the input in that is going to that's really going to bite me. Everything else I'm good at, I promise. I'm not really, but you know, do what I can. So let's get the actual puzzle input here. I accidentally named it a little weird here, but we'll fix that. Okay. So this says that the value on the accumulator is 1723 when we go into an infinite loop. So let's put that in the puzzle. Okay, we got it right. At long last, after messing around with string parsing, as always seems to be the case with me. Part 2. After some careful analysis, you believe that exactly one instruction is corrupted. Somewhere in the program, either a jump is supposed to be a nop or a nop is supposed to be a jump. Accumulators are always the same. The program is supposed to terminate by attempting to execute an instruction immediately after the last instruction in the file, so we run all the way to the end. By changing exactly one jump or nop, you can repair the boot code and make it terminate correctly. Change the first instruction from nop plus 0 to jump 0. It could create a single instruction infinite loop. Change almost any of the jump instructions, the program will still eventually find another jump instruction and loop forever. However, if you change the second to last instruction from jump -4 to nop -4, the program terminates. Okay. Okay, so we need to change the program by changing exactly one jump to nop or one nop to jump, and then find the value of the accumulator after the program terminates. So, let's see how big the input is. That's not what I meant. Okay. Program has 650 some instructions, so it's not inconceivable that we brute force this, but I want to think about doing something a little more elegant than that. If we can try and backtrack from the desired end state of the program to find some way to reach there that that doesn't some way to reach there by flipping one of those instructions. So, well, first thing I'm going to do is copy our part 1 code to part 2, so we can start with that. Okay. So, so I'm thinking about this backtrack. So we want to be at the position of 1 after the end. I'm thinking, I might actually try and just see how far we get by brute forcing this, because there's on the order of hundreds of instructions. It might, and computers are fast, but there's probably a more elegant way to do this, but I'm just going to see where we get with brute forcing. So this version of run program until end, if it does get into an infinite loop, I'm going to have it return null op saying that we didn't get to the end, but if it actually gets to the end, then we are good. So we'll say if we succeeded in that case, if we're visiting the same instruction again, we've got a problem. And so now we will try and try all opcode flips, we'll say. So what this will do is we're going to for each instruction, if it's either a jump or a no op, we're going to try flipping just that one opcode, and then we're going to try feeding it into this run program till end function and see if the program actually terminates. So this is an exhaustive search. It may not be the most elegant thing, but I think that it's still it may still be fast enough, even though it is brute force. So we will switch on the opcode as we typically do. If it's accumulate, we know that none of those were flipped, so we just continue. We skip to the next iteration of the loop. There's nothing to do there. If it's a jump, we will change the opcode to be a no op. We will then try and run the program to completion, the modified version of the program to completion. And if that succeeds, then we will go ahead and return the ultimate result that we get. If not, we just have to remember to set the opcode back to what it originally was, which was a jump. And we will continue on to the next iteration of the loop. And for no ops, it's just a mirror image of this. Jump bypasses variable initialization. Yes, we will put those in there. So we switch a nop to a jump. See if it gets us where we need to be. And if we go through all the instructions and we don't find anything, then we failed and we haven't gotten what we needed. So let's, I think this is all we need for the solution for part 2, the brute force solution. As they say, when in doubt, use brute force. A key part of the Unix philosophy. So let's see what it does with the test input first. We'll see if it gets the right answer for the test input. So for the test input, it says 8. Yep. So that is the correct answer according to the puzzle input. And that ran still really quickly. We got to our supposed answer of 846. Now let's see if that's correct. All right. That is day 8 completed. Brute force. Works every time. Let's go ahead and see where we are on the leaderboard. I have to imagine, because of the screw-ups with the string parsing, that we did not do too well on the leaderboard today. Yep. Yeah. One of our worst days so far, at least for part 1. But, hey, that's okay. Reviewing this, clearly, the big mistake that I made tonight was just not using these old school C-style stir comp instructions correctly, because they give you a signed value depending on, whether the left side or the right side is before or after in lexicographical order, and it's 0 if they're equal. And I was doing exactly the opposite. I was instead of comparing these to 0, I was just using this as a Boolean conditional, so I was doing exactly the opposite of what I wanted to do with the parsing. So that was what messed me up and slowed me down the first time. I'm sure for some of you watching, it was a little bit painful to watch. You may have seen the mistake that I made, but hey, we saw that. And maybe that's a sign to me that I should shy away from using this old school C stuff that I use less frequently, and just convert things into C++ classes like string view before I do string comparisons. For part 2, you probably heard me thinking aloud about non-brute force ways to approach this problem. And in particular, I was thinking, can we backtrack through the traces of the problem? Can we sort of reverse engineer from the state that we want to be at, which is 1 past the end of all the instructions, and try and find all of the incoming pass through the code that could go there. So all the sequences of acts and nops at the end of the program, which would lead up to that final instruction of the program, or different jumps elsewhere in the program that could lead there, and try and find, the one change in the control flow graph of the program that would make everything correct. I think that sort of approach is still possible. I haven't really thought too much about what the algorithmic complexity of that is. I can say just right now that that our current solution, the time complexity of it with the brute force is n squared, because this outer loop trial opcode flags revisiting each instruction once to try and toggle it, and then the inner loop is this run program until end, and run program until end will visit each instruction in the program at most once. So, that's visit every instruction once on the outside, visit every instruction at most once on the inside, multiply them together, you get your n squared time complexity. And when we have a program, our test input, that's only 653 instructions long, n squared is not too crazy bad. The computer can just blaze through it very, very quickly. So this is one of those cases where, brute force works just fine. I might think a little bit more about, different ways of trying to actually build a control flow graph through the program to try and solve it in a way that isn't necessarily brute force or doesn't have n squared complexity. But I'm still, reasonably happy with the brute force solution that we came up with tonight. So, yeah, I I think that that'll about do it for tonight's stream. You can always find replays of these streams up on my YouTube channel. That's at youtube.com/spoonboy42. If you happen to be watching a replay on YouTube, you can, if you are actually up at night when these puzzles unlock and you want to see the live stream, you can see it on my Twitch channel. That's twitch.tv/spoonboy42, link down in the description. And as always, the source code for these solutions goes up in my GitHub. That's at github.com/craig-chasser/AOC2020. Once again, link in the description. Check it out. Thank you to everybody who has joined the stream tonight. Thank you to everybody who is, working through these puzzles, having fun as a community. And I will... So I'm not sure if I'm going to be able to stream tomorrow night. Hopefully I will be able to, but assuming that I am able to, I will see you again tomorrow night. Otherwise, I'll see you all on Wednesday. Thank you again, and happy coding.